How do you intuitively understand system stability analysis? Imagine you're balancing a pencil on your finger. If it stays upright, it's stable. If it tips over easily, it's unstable. This simple picture helps us grasp what system stability analysis is all about. In electrical engineering, especially in control systems and power systems, it's about figuring out if a system will settle back to normal after a disturbance or if it will spiral out of control. Think of it like a ball in a bowl. If you push it gently, it rolls back to the center. But if you push it too hard on a hilltop, it might roll away and never come back. That's the core idea of stability. When a system experiences a disturbance, like a sudden change in load or a fault in the power line, stability analysis asks whether the system will return to its original state or drift further away. It's like checking if a boat will stay steady after hitting a wave or start rocking wildly. The key is understanding how the system's components react to changes. For example, in power systems, the rotor angles of generators act like a mass attached to a spring. The inertia of the rotor resists sudden movements, and the electrical power transfer acts like a restoring force. If the rotor angles stay within limits and oscillate gently, the system is stable. But if they diverge, the system risks losing synchronism, which can lead to blackouts. There are different types of stability to consider. Steady-state stability looks at small, slow changes like increasing the load gradually. It asks if the system can keep running smoothly under these conditions. Transient stability focuses on big, sudden events like faults or switching operations. It checks if the system can hold together immediately after these shocks. Dynamic stability involves oscillations that happen over seconds or minutes, and whether these oscillations damp out or grow over time. Mathematical tools help us understand stability better. Time domain analysis simulates how variables like voltages and currents change after a disturbance. If the oscillations die out, the system is stable. If they grow, it's unstable. Frequency domain analysis uses eigenvalues and damping ratios to identify how different oscillation modes behave. The swing equation models the mechanical motion of generator rotors, helping us see how they respond to disturbances. Power system dynamics are nonlinear because power transfer depends on the sign of the rotor angle difference. This means stability can be maintained up to a point, but if a disturbance is too large, the system can lose stability. That's why engineers set limits and design controls to keep everything within safe bounds. Practically, stability analysis guides the design of protective relays and control devices like voltage regulators and governors. It helps determine how quickly faults must be cleared to prevent cascading failures. It also supports planning for integrating new energy sources like solar and wind, which can cause fluctuations. By understanding how the system responds to different disturbances, engineers can keep the power grid reliable and safe. In essence, system stability analysis is about predicting whether a system will stay in harmony after being pushed. It combines physical intuition, like the ball in the bowl or the rotor on a spring, with mathematical models to ensure everything keeps running smoothly. This way, electrical systems can operate safely, even when surprises happen.